the cement. No, come on, you're the only one with the backpack, right? Who's from the system? Siri, set a timer for 2 minutes.
2 minutes starting now.
All right, gentlemen, let me see. So we still got like a little over a minute.
In being in the Atlanta University.
Siri, stop. See the time. Yeah, we still got a little over a minute. So I'm just kind of watching the clock. 30 seconds. Matt, stop. Thank you. Gonna make me throw up. Sorry, guys. Dog is over here being disgusting. Not really disgusting. I don't know the proper phrase. definitely makes me gag. Okay, anyway, let's see. I think we're. Yep, it's that time, right? Where's the clock? There it is. Okay. Okay, so I'd rather stand.
Defense, passing the ball. You.
All right, gentlemen. Let me see. So, welcome. All right. So, with today's lecture, we're going to be closing out chapter 1. Right. So, a somewhat accelerated pace to start. The pace will slow down. We still got a little ways to go though. But yeah, so today will be the last of chapter 1. So hopefully you guys are, making your way through Pearson. Pearson is a really good tool. Like I go out of my way to make sure that we're using Pearson. I think it's the most user-friendly like online learning management tool. Shameless plug for Pearson. Especially because of their learning aids, like with each homework question, they usually come with like a viewing example. Sometimes they have video and animations to explain the question or the concept. But the viewing example, what it does, it gives you the same question that you're working on, with different numbers. And they I would say at least 90% of the homework questions basically have the explanation behind the concept attached to each question. Then it has the ebook right there, so it takes you directly to the section or whatever. And then also it has the feature of the ask my instructor. So with that, it'll send me a screenshot of your question. So, after you've done what you can on your own, you've done what you can, with your peers, you've done what you can with the tutor, then after all of that, if it's still not sinking in, that's the best time to ask me. That's the long and short of it, right? So, anywho, there's more to that story, but for the sake of time, I'll just cut it there. Let me see. So yeah, just the main thing is that you're gaining, or that you already have full access to Pearson, and that you're making your way through those assignments. Also, with our assignments in Pearson, keep in mind that we get unlimited attempts on all assignments. The system is set to take your highest score, and I think there's a 10% late penalty. I just forgot to change. I'll try to look at it. If I can remember. And I already know I'm not going to have energy, but because usually when I get out with you guys, I just want to crash and go to sleep for a while. But if I can remember, I can check the late penalty. I'm open to changing as many of them as I can to 5%. So we'll see. It's just a matter of me getting in there before you guys started. I can't think of anything else that's major, right? So let's. Are there any questions? Let me just pause for the calls for a moment. If you have questions, now's a good time to kind of ask them. As we kind of go through the presentation, if you have questions, it's probably best to use the Q&A. I'm monitoring the chat. I'm monitoring the Q&A. I can barely get that word out. I feel like there was something else. Yeah, that's the meat and potatoes. So last time. So last time we started exploring a lot of the shortcuts, a few of the shortcuts regarding finding the derivative. So a few key points, right? So one, if you don't get anything else, at least the takeaway is the derivative is going to be the slope of the tangent line at a point. We introduced the concept of derivative by taking the limit definition of the difference quotient. The limit is h tends to 0. That's just for introductory purposes. Last time on Monday, we explored the shortcuts, right? So we had the power rule, right? So when we take the derivative of a power, the power comes down, we subtract 1 from the power, and that's the derivative. Instead of that whole long page of calculations and algebra, right, from the limit definition, now we're exploring some more sophisticated techniques for finding the derivative. And so that's what we're going to be doing today, exploring more of these techniques. So we talked about the power rule. We also talked about power and we talked about the sum difference rules and the product rule and the quotient rule. Right. So, and we're going to be doing more of that today. It all kind of compounds. It kind of stacks, So anyway. Okay. And again, if you have questions, feel free to either unmute yourself or type in the chat or the Q&A, and we'll make sure that it gets addressed. I'll make sure to address those inquiries before we leave. Okay. All right. So again, we should be closing out chapter 1 today on differentiation. Again, the derivative is just the slope of the tangent line at a point. And so we're going to start off with section 1.7, the chain rule. All right, we're going to start with the chain rule. Okay. So a few objectives: find the composition of two functions, and then two, differentiate using the chain rule. Right. So from college algebra, sorry. So from college algebra, composition of two functions. Right. So one function inside another function. So given some f of x and some g of x, you're going to have one function that's going to replace all x's in the other function, and so that kind of lays the foundation or the baseline for where we're going to start with the chain rule, right? So suppose we had a composition of functions where we had one function inside another. How would we take the derivative of that guy, right? Okay, so that's what we're going to be exploring here. So the composed function f composed g, the composition of f and g is defined as f composed g. Again, this composition symbol is like an open circle, right? A lot of times that's the student's first time. It should not be your first time seeing it if you're in calculus, because you should have seen it in college algebra and pre-cal. But the open circle, that means f composed g, right? So the second function inside the first function. All right, so like if we were writing this out, whatever our f of x is, we would write it like normal. Then we would replace each x with a blank set of parentheses, and then we would put the function g into each of those blank parentheses. All right, let's see if we get an opportunity to do this again. So given this f and this g, we're asked to find f composed g and g composed f. Right. So we're at least going to get an opportunity to revisit or recap composition of functions. Right. Okay. So let's start with f composed g. So f compose, I'm going to do this, g of x. Again, this means the second function inside the first function. So it's going to be f of g of x, right? So what this means is all I'm going to do is write f of x like normal, but wherever there's an x, I'm going to replace it with the green thing, right? Okay. So then this is going to be f of, now g of x is 1 plus x squared. Okay. All right, let me see. Hey, Google, set a timer for 25 minutes.
Got it. 25 minutes. And that's starting now.
So that way, because we're trying to break, half the class is 1.7, the other half is 1.8. Okay. All right. So again, we just write f of x like normal. So that would be x cubed, but I'm going to replace x with a blank set of parentheses. And inside the blank parentheses.
Tell me a shout.
Okay, so it's going to be 1 plus x squared. Okay. We probably should, for the sake of time, I'm not going to expand it out because you should be able to expand it. But that's just there. I think I can do it. Let me see. I don't think that they expanded it. I just want to glance. Okay, they did expand it. Let me just go ahead and expand it. It shouldn't take too long. I think the way it goes is going to be like a 1 plus, let's see, AB squared. So let me see. It's going to be 3 x to the 4 3 x squared.
Again.
And then plus x to the 6. And I'm going to just rearrange it. I mean, it's where? Oh, how did I get an extra one? Oh, no, we're good. We're good. So let me check on this. Well, let me go ahead and do the second one. So again, we're just cubing. I think the shortcut for cubed is like the first term cubed, and then 3. It's like 3ab squared plus 3a squared b plus the last term cubed. I think that's the shortcut for cubing something. Okay, anyway. So then let's do G compose F. This means the second function inside the first function. So this means G of f of x. Okay. What's our f of x in this case is x cubed. So our g of x is 1 plus x squared. And again, we're replacing each x with x cubed in this case. So then that ultimately looks like it's going to be x to the power of 6 plus 1. Okay, let's see how do we do. 3x squared, 3x to the 4, x to the 6. Okay, yeah, we're good. Okay, so again, hopefully there aren't any questions on this one. Let me check the chat real quick. So the chat and the Q&A looks good, so we're going to keep going. Okay, so for this F and G Moore composition, okay, sure. So then, I'm tempted to leave this as an exercise, just for the sake of time. Let's see the time. We can do it. It won't take that long. So then, F of G of x, all right? F compose G. F compose G of x. Again, this means the second function inside the first function. So this means F of G of x. Okay. Okay. So then this means G of x is, in this case, x minus 1. Then our f of x is the square root of x, so we would say the square root of x minus 1. Okay, so let's do G of f of x. Sorry. So this means G of f of x. So f of x in this case is the square root of x. So it's going to be x minus 1, but our x in this case is going to be square root of x. So I think the main takeaway with these examples, notice that the order is important. If we change the order of the composition, we're not guaranteed to get the same result. In some cases, you do get the same result, but it's not guaranteed. So the order is important when we're doing composition of functions, right? Okay. All right, these are good. Okay. So the chain rule. So in the previous example, we revisited composition of functions from college algebra 1. And so now suppose we had a composition of functions and we wanted to find its derivative, right? And we wanted to do one of these shortcuts and avoid the whole limit definition of the difference quotient. So the derivative of a composition, f composed G, is given by the derivative of f composed G is going to be, long story short, is going to be the derivative of the outside function times the derivative of the inside function, right? So in other words, you can look at it like you take the derivative of f, but those results, you're not going to write x, you're going to write g of x in place of the x's. So it's almost like you can it looks like you can find a derivative of f by itself, find a derivative of g by itself, but then for your answer for f, you got to replace the x's with g of x. That's what it looks like. But again, the way I learned it was the derivative of the outside function times the derivative of the inside function. Let me see. Let's look at this example. So for this y and this u, find dy by du by dx, and dy by dx. Okay. So the first one, dy by du, that means the derivative of y with respect to u, right? We already have y in terms of u, so we just take the derivative. Okay. So for this one, whenever we take the derivative of y, we're going to write dy by du. So then our dy by du, for that first term here, remember, I think last time we said the derivative of a constant is 0. So when we go to take the derivative, that guy is gone. Then we take the derivative of square root of u. Keep in mind that square root of u is the same as u to the power of a half. All right? So then when we go to take the derivative, the power comes down and we subtract 1. Okay? So then that result should be what? 1/2 u to the power of a negative 1/2. I'm going to leave it like that for now. Okay? So that's the derivative of y with respect to u. So let's find the derivative of u with respect to x. So we're going to use the second equation. So du by dx. Okay. So just take the derivative. So x to the power of 3, right? From last time, the power rule, again, the power just comes down and we subtract 1 from the power. So the derivative of this term is going to be what? 3x squared. And the derivative of a constant is 0. Okay. So this was our first result. This is our second result. And then now for dy by dx, what we can do is the following. So let me see. If we want to find dy, the derivative of y with respect to x, can't write today. What we can do is take our dy by du, and we can say times du by dx. Okay. So essentially what's going to happen, these expressions are going to cancel. So let me see. If we translate that, that's going to be what? This 1/2 u to the negative 1/2 is going to be that expression times 3x squared, right? But there's one more step we need to do here. One more step. Again, we want the derivative of y with respect to x, and we still have this u there. So we need to find an expression where we need to find u in terms of x, which was given. So we need to replace u with the original function, right? So I'm going to move that to the denominator. It looks like it's going to be 2 times the square root of x cubed plus 1, okay, under 3x squared. Okay. So this is our derivative of y with respect to x. So again, I think that observation that we made before it seems accurate, right? Where we took the derivative of y, we got the 1/2 u to the minus 1/2. We took the derivative of u, we got that answer, and then we just multiplied our answers, but we had to go back and replace the u with the full function, right? So I think again on this previous slide we said just the derivative of f, the derivative of g, but from that answer from the derivative of f, we got to replace the x's with the inside function. So we did the exact same thing here. We took from the derivative of that first term, we had to replace the u's with the full function, right? So now our final answer is the derivative of y with respect to x. There's no u's, it's only x's, right? So the best way I can summarize that is the derivative of the outside function times the derivative of the inside function. Let's see, hopefully we can get another example. I kind of want to do another one. Here's a typed version of what we just experienced, and I think we got the same thing. Okay. Quick check I'm going to leave as an exercise for you. Okay. So given this y and this u, find, okay, the derivative of y with respect to t. Let's give it a go again. So we asked and we shall receive, right? We wanted another one, here's another. Okay. So we want to find the derivative of y with respect to t, but y is given to us in terms of u, and u is given to us in terms of t. So if we want the derivative of y with respect to t, we got to do the following. Basically the same thing we did in the previous example. So again, if we want the derivative of y with respect to t, we can do the derivative of y with respect to u times the derivative of u with respect to t. So du by dt. Okay. Okay, so if we do this, okay, let's keep going. So what's our derivative of y with respect to u? So that derivative, the 2 comes down, so that's going to be 2u minus 3, okay? Times the derivative of u with respect to t looks like it's just going to be a 5, right? Because the first term, this derivative of this guy is just 5. The derivative of this guy is 0, right? So 5 plus 0 is just 5. So now we need to go back and plug in, we want this in terms of t, so we need to replace u with the full function in terms of t, okay? So this is going to be 2 times 5t minus 1 minus 3 times 5. And let's just simplify this. So first I'm going to distribute this 2. I'm going to go ahead and distribute this guy as well. You might be better off doing it in 2 separate steps, but let me see. 5 times 2 will be a 10. Times 5 is 50. 50t minus 10 minus 15. I think that's right. Because that would have been a 10 minus 2. And then it became a minus 5. Let me keep going. This looks good. I feel confident about this. So 50t minus 25. So what we're saying is that the derivative of y with respect to t should be 50t minus 25. 50t minus 25. And I think they did the exact same thing we did. So, okay, our timer should be going off pretty soon. We have this theorem. Let me check the chat real quick. So the Q&A and the chat look good. Let's keep going. So theorem 10, the extended power rule, right? So again, power rule, we've been working a few of these kind of repeatedly between Monday and today. So extended power rule is like if we take the power of a function. So extended power rule is like a combination of the power rule with the chain rule, right? So suppose that g of x is a differentiable function of x. Then for any real number k, the derivative with respect to x of g of x quantity to the power of k is going to be k. Basically, it's like the power rule with the chain rule. The power comes down, you subtract 1 from the power, times the derivative of the inside function. In other words, just like the chain rule, derivative of the outside function times the derivative of the inside function, right? So the extended power rule is like a special case of the chain rule. Okay? All right, let's keep going. So given this, we're asked to find a derivative. So again, derivative of the outside function times the derivative of the inside function. Okay? So then our f prime, the 1/2 comes down. The inside stays as is. That's going to be now become a minus 1/2. We're going to say times the derivative of the inside function. The derivative of 1 is 0, plus the derivative of x cubed is 3x squared. That should be sufficient. We could get rid of the negative power by rewriting it as the square root 1 plus x cubed. There's a 2 here, and 3x squared. I feel like there should be questions. You have any questions? Again, feel free to either unmute yourself or type in the chat if you have question.
Tell me, am I too grown for that shit?
I'm gonna make it so that you guys, I don't know why you keep unmuting yourself. I'm gonna make it so you can't unmute yourself. Okay, anywho. Okay, so we got 3x squared over 2 root 1 plus x cubed. Let's see. Yeah, we're good there. Okay. So chain rule, extended chain rule, or extended power rule, derivative of the outside, the derivative of the outside function times the derivative of the inside function. It takes a little bit of practice to get used to, but once you get used to it, it becomes second nature. Honestly, between yesterday and today, a lot of these become second nature. Like, it might be a little jarring initially, but fairly quickly, like within about 2 weeks, it should just be like, okay, those should be no problem. Because we do so much of those, so many examples, like using those techniques, it really does become second nature. Okay, so now we have an application, I think, of all the techniques we've talked about. Right off the bat, I see extended chain rule. I see the product rule, right? So let's go ahead and do a quick recap on the product rule from Monday. Product rule was what? Let me see. The first times the derivative of the second plus the second times the derivative of the first. All right, okay? So let's see that in action. So then our f prime, in this case, the first function of just copy, this is just a copy. Yeah, the first times the derivative of the second. So I'm going to put, I'll do d by dx, right? So times the derivative of the second function, which is going to be this guy. So I haven't taken a derivative just yet. So the first times the derivative of the second plus the second times the derivative of the first. So times d by dx of this guy. Okay. So now we need to go and find the derivatives of those parts in green. So the first part just comes down, just a copy. Okay. So the derivative of this is extended chain rule, right? So the 10 comes down. When we go to take the derivative, this guy comes down. We subtract 1. Same thing here. Power comes down, and we're going to subtract 1. Okay. So this is going to give us a 10. We're going to have this 7 minus x to the power of 9. And I think we need to say times the derivative of the inside function. In this case, it looks like it's a minus 1. Okay, so it's a lot to keep track of, right? So give yourself plenty of space. Take your time. We still got a whole nother one to go over here. I'm going to say plus like this. Okay. I'm gonna do the derivative part in green just to help for the organization. So you know that that's what we took the derivative of. Okay, so then 7 minus x to the power of 10. Can't write today. Now the derivative. So the 4 comes down. 3x minus 5 to the power of 3 times the derivative of the inside function, like it's just 3. Okay, so then we need to come back and simplify. Now I think we have some like factors that we can factor out. I'm going to shrink this down just to get it on the one line, just because I'm working on a digital space and I can do this. So I'm just doing it because I can, and that would have been my goal all the while anyway, is to get it on one line. Okay. So now we could expand this out. Obviously, I'm not going to do it with powers of 9 and powers of 10, but we have some like factors that we can factor out. It looks like they both have that's a minus 10. Okay, let's start with our numbers, right? We got, what, a negative 10, and we have 12. So the greatest common factor, let me see, is 2 and 5 and 2 and 6. So it's a 2. Okay, so it looks like we can factor out a 2. 3x minus 5, let me highlight it. this has a 3x minus 5, and here's another 3x minus 5. Here is a 7 minus x, and another 7 minus x, right? Okay. So then we're going to have this 3x minus 5. What's the smallest power? It's power of 3. So they both have at least 3 of those guys. And then they both have this 7 minus x, and they both have at least, what, 9 of those guys. Okay. So then we need to capture what's left over after we factor these guys out. Okay. If we factored out a 2, that means it looks like there's a negative 5 left there. Let me see. So it looks like this is gone after we factor. And it's only one of those guys left. So 3x minus 5. So it looks like it's easy to lose track, right? So you just got to take your time, give yourself space, and slow down, right? Let me see. So from the second term, 3x minus 5. So that one's gone. We took all 3 of these guys. And I think we had one of the second one left over. Let me see, a plus. It looks like it's if that was 12, we factor out a 2, so it should be 6 times 7 minus x. Okay, I think we got one more step. Okay. So then ultimately, it looks like we're going to have this 2. I'll just keep my colors for the sake of simplicity. 3x minus 5 cubed. 7 minus x to the power of 9. My dog is still back there munching on something, and it sounds so disgusting. It's like while I'm trying to like concentrate and think, I just hear. It just makes me want to gas. Yeah. Thanks. It's distracting. Thank you. She just looking at me like, what? What, did I do something wrong? What did I do? Okay, let me see. Oh man, I should have did this before. Okay. So let's focus on the x's. That's what a negative 15x minus 6 looks like it's a minus 21x. Now I might be going a little bit far, but it's okay. So I think those together looks like it's a minus 21, right? Minus 21x. That's going to be a 25, 42, 20, 25 and 42, 65, 67. Hey, Google, stop. Okay, I think this is it. I'm gonna leave it like this. Hopefully we didn't make any mistakes. This looks decent, but yeah, I mean sometimes they come out weird like this, right? Okay, let's look at our prepared notes and just see how do we do. Okay, and so like with the structure of this course, especially with it being a remote and the way I have it designed with like the unlimited attempts, you know, I'm like removing some of the rigor, and it's like, you know, I know this stuff can be intimidating. It can be daunting if you don't know how to like slow down and like space it out and stuff like that. So like, I really want you guys to just do your best, right? Like just try and just keep trying. Like don't take it too serious. Like, you know, be prompt and like get everything submitted, but just do the best that you can. Like that's why I intently put the unlimited attempts. You get it wrong, try again. Use the energy of until, and you can ask for help and you can collaborate. Like it's totally okay. You know, but just try to learn as much as you can and just do your best. Okay, let's see how do we do. Okay, simplify. 3x minus 5 cubed, 7 minus x to the 9, 67 minus 21x. Wow, right? So what we did was correct. You know, it just, you got to slow down, take your time, go one part at a time, get a lot of space, like either a dry erase board or, you know, plenty of blank paper. I'm working in a digital space. I don't know how many of you guys have like tablets or anything like that, but you know, I love the tablet because it's unlimited space. So as long as essentially nearly quote unquote, you know, as long as I have power, then I have paper and markers and all of this. Versus, I mean, I like the feel of like paper and chalk and all that, but I have to like, that's a whole nother thing. This is just much simplified. This is my gaming, movies, work, like I do it all in one, right? It's a lot of fun. Okay, so yeah, we got that one. Okay, and it is time to go into the next section. I think we got a little bit more. So that was fun. A quick check, and yeah, we made it to the end of that one. Okay. So this was the chain rule, and I'll make a copy of these notes at the end of class. Um, the main takeaway with chain rule is that it's like the derivative of the outside function times the derivative of the inside function. Okay, so it takes a little bit of practice, but it's doable. Now then the trick comes, in stringing all these concepts together. I think individually they aren't too bad, but then you saw in that last example, you could string them together, and it can get kind of dicey fast, right? When I was a student at Morehouse, there was this poster in the hall. I don't know, for whatever reason, it's just like etched in my memory. It goes something like this: like, there is no such thing as complicated or as complex. What we consider to be complex is just a long string of simple ideas, right? So, if you were to look at my work, this looks complicated, but in reality, what this is just a long string of simple ideas, right? The simple ideas we've been talking about from yesterday and today is just put in one long string. But if you're missing one of those simple ideas, then that's where people tend to get lost and get intimidated by this kind of stuff, and then they shut down and they don't try. So again, this is why it's important to slow down, ask for help, collaborate, and you just got to take it one part at a time. Like, don't try to do it all at once. Just do it one part at a time. And if you can just keep taking those incremental baby steps, you can digest the whole thing. My dad used to say this quote: "How do you eat an elephant?" Anybody knows how to eat an elephant? The answer is one bite at a time, right? So that's indicative of what this was, all right? So one part at a time. Last little story, then we'll get back on track. There was this TED Talk video that came up, and this guy, he opened with like talking about drawing and like these like high, super realistic like black and white drawings. And so he described how he was doing. And like he'd have an image and he would, break it down to a little square. And he was like, well, can you draw a dot? Can you draw like a black dot? Can you draw a gray dot? If you can draw a dot, you can draw these things. And he was like, the trick is, again, just like eating an elephant, you got to break it down to digestible pieces. So when you look at the big picture, it looks like super detailed, and you're like, yo, how did you do that? But he's like, look, I just break it down to the smallest units that's digestible for me. And so he launches into like all these grand feats that he's done, but in reality, he's just doing small pieces in a long chain, like, walking cross country. I literally know a guy that bikes across countries like America, Europe, him and his dog on his bike. That's just what they do. And like, I'll go running. You might catch me on like the belt line, like, and I'll run across the city for like 20 miles, 10 miles out, rest, turn around, come back. But the trick is, it's like, again, it's just one step at a time. I'll take snacks and stuff to make sure I can, stay in the elements. But it's just one, and you get into like this rhythm, and it's like, it's just one step at a time. This is the same thing. So if you can master that thing of slowing down, break it down into a digestible piece for you, right? He was talking about like books that he would read. He was like, okay, his first goal was like, okay, let me read a chapter a day. And he was like, if that felt too daunting, he was like, okay, well, let me read a paragraph a day. He's like, if that's too daunting, okay, let me read a sentence a day. He's like, okay, let me read one sentence and then I'll take a break. And then I'll come back, let me read another sentence and I'll take a break. And so it's like, over time, he eventually reads all these books, right? He completes all these tasks. So the takeaway is, breaking these big tasks down to digestible pieces for you, right? That's something that's personal. It's not nobody else's place to say what's digestible for you. It might be one letter at a time, one sentence at a time, one variable at a time, one equation at a time, one assignment at a time. It's different strokes for different folks. Okay, so enough of the pep talk. Okay, so we got a solid 30 minutes, give or take. So we're going to go ahead and move into the last section for chapter 1. So hopefully you got something from that little mental adventure we just went on. Let me change my view. Single page. And I'm also saying this for myself. Like, I know I'm like chatting with you all, but I'm saying this to myself. And I was like, when I think about it, that's honestly what I've been doing. But I just be distracted by gaming all the time. But I kind of keep it going intently because I know that there's something there that I can actually help the world with, that I'm learning from those encounters. Like, if it's not patience or determination or embracing the energy of until. You know, it's a lot of things that I learned in these encounters, especially with Mobile Legends and like gaming with people around the world, and the frustration and learning how to manage the different energies. It's really fun. It's really interesting. Okay, so the last section for chapter 1 on differentiation is section 1.8, higher order derivatives. Right. So we've explored. We've introduced the derivative, the slope of the tangent line at a point. We introduced how to find it using the limit as h tends to 0 of the difference quotient. That was kind of long and drawn out. Then after that, we explored some shortcuts. Instead of having to use the limit definition, we explored the power rule, the sum and difference rule, the product rule, quotient rule, chain rule, and extended power rule, right? So this was taking a derivative. Let's see, what do we mean by higher order derivatives, right? So a few objectives here. 1, find derivatives of higher order, and then 2, given a formula for distance, find velocity and acceleration. Okay, so higher order derivatives. Consider the function given. Its derivative is what you see on the second line, right? So we have y equals x to the 5 minus 3x to the 4 plus x. Then its derivative is 5x to the 4 minus 12x cubed plus 1, right? So the derivative function f prime can also, so the answer that we just generated, it also can be differentiated, right? So we had an original function, we took the derivative, we got an answer. Now we can take that answer, and in this case, we can take the derivative of the answer. So now we can talk about, that's called the second derivative, right? So we can think of the derivative f prime as the rate of change of the slope of the tangent line of f. It can also be regarded as the rate at which f prime is changing, okay? So we use the notation f double prime for the derivative of f prime, right? Yeah. So that is f double prime is d by dx of f prime. In other words, f double prime is the derivative of f prime. We call f double prime the second derivative of f. So given some y, given this function y, the second derivative is going to be this guy, right? So higher order derivatives are basically derivatives of derivatives, right? How far can you take it? Some instances is infinite, some collapse to 0, right? So for higher order derivatives, we use the notation f, the nth derivative of f, to express the nth derivative of f. Continuing in this manner, we have the third derivative of f is this guy, the fourth derivative of f is this guy, the fifth derivative of f is this guy, right? So for this function, we have the third derivative, fourth derivative, fifth derivative. Now notice with the sixth derivative, it collapses to 0. And then any nth order derivative higher than 5 is going to be equal to 0 for any integer greater than or equal to 6. So higher than 5 or greater than or equal to 6, same thing. All right. So higher order derivatives, the simple thing is the derivative of the derivative. Okay. So Leibniz notation for the second derivative of a function is given by the second derivative of y with respect to x. So d by dx of dy by dx, right? The derivative of the derivative. This is read the second derivative of y with respect to x. The 2's in this notation are not exponents, right? So again, when we see this second derivative of y with respect to x, it just means take the derivative twice. So it is kind of easy to think as the power is not a power, right? It just means take the derivative twice. That's all it means. Okay. All right. We're gonna let that be. So given this y, we're asked to find the second derivative. Okay. So yeah, now sometimes these just buckle up, Buttercup, because these kind of get a little bit dicey too as well. Give me just a moment. So yeah, before class, I recently discovered, like, I don't know, I'm probably gonna gain a bunch of weight, but from Zaxby's, they got this chicken Philly. I was like, oh my god, that shit is so good. It's so good, and like, but I get them to make it without cheese. I don't know, this stage of my life, I've been avoiding cheese, and it still had a little bit of dairy, but I can't do cheese like that. And I'll take it as far as, like, sometimes I'll get like the personal pizzas from Quick Trip, and I say, hey, make it with no cheese. And it's just it gets the job done, but something about the cheese is just like my body is like no. It's like my body responds like it's instant poison. I'm not saying anything for anybody else. I'm just saying for me, I can't do cheese anymore. So a lot of times I live vicariously through others. Like when I'm out and they're eating cheese and their pizza, the smell of it is enough for me, and I'm like okay, but I can't do the mucus and I can't do it anymore. So those I had my fond memories. And one thing that's so funky or weird or interesting about cheese is it's like one molecule away from heroin. It's practically heroin. It's just a low dose or whatever, so it's not really addictive. Well, it is addictive. That's honestly what's really going on, but it's not like deadly like the actual drug. But people are addicted and they don't even know it. That's part of the marketing of like pizza and cheese and all this. And so I mean, this is just something I heard from a long time ago, but that's not why I stopped. It's just again, I can't process dairy like that. But anyway, that's neither here nor there. Okay, so we want to find the second derivative. All right, so let's start by finding the first derivative. So we have our y. So we want to find dy by dx. Okay, so we could use the quotient rule, low d high minus high d low over low low, right? So in other words, if we were going to use the quotient rule, we could say the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. But instead of using the quotient rule for the first derivative, I think I'm going to rewrite that as a power, right? So I'll go like this. This is equal to x to the minus 1. And so now when we take the derivative, we can bring the power down and subtract 1. Okay. So ultimately we'll get a negative x to the negative 2. Okay. So that's the first derivative of y. Power comes down, subtract 1. Okay. So now for the second derivative, so the second derivative of y with respect to x, this means d by dx of the first derivative. So in other words, take the derivative of the derivative, right? So let's apply the same rule. Let's apply the same, this again, this just means d by dx of this negative x to the negative 2. Okay, I'm going to continue working over here. So if we take the derivative of this guy, kind of doing this similar technique, power comes down and we subtract 1. I think we got lucky with this one. It's going to be what? So 2x to the minus 3. Now, see, I think if we tried to do the quotient rule, that was going to be way more complicated, right? With these examples and these techniques, you try one thing. If it doesn't work out or if it seems like it's getting worse, scrap it and then try something else. Try a different technique. You know, there's more than one way to go about these. Sometimes it's unavoidable, but then sometimes it's just a matter of trying a different technique. Okay, so then here, do something like this. Okay. Oof. And then it's like I'm getting older, so it's like when the weather be changing, I get aches and pains in the body. I was like, "What is this?" And it just dawned on me today. I was like, "Oh, it's probably because it was cold." And I'm like, "That's why I'm getting aches and pains." You know, it's like so I'm always studying like foods that help remedy these aches and pains and things like that. And so, you know, stuff like that. Okay, I think this is okay. This looks good. We got 2 over x cubed, which is good to go. Okay, let's do another one. So for this function, we're asked to find y prime and y double prime. Okay. So we're given a y. So let's find y prime. It looks like the extended chain rule or extended power rule. So again, if we're going to find the first derivative, power comes down, we subtract 1. So that's going to be what? 20. This persists. Power is now 19 times the derivative of the inside function, 2x plus 10. Okay. Oh, see, I can already see it now. So now we need to, when we go to take the derivative of the derivative, take a moment to see what technique we're going to have to use. Anybody see it? All right. I'm going to simplify it just a little bit first. Would that make it easier? Because I can factor out the 2 and turn that into a 40, and the right-hand side would be x plus 5. And then when we go to do, hopefully we're thinking the product rule, that constant we can just move to the front. So I think I'm going to do that. And just for the sake of space, I'm going to do it here. I'll do it in purple. This was a 5. We factored out 2, so that makes this guy a 40. I'm just doing this for the sake of space. Okay. I just rewrote. All I did was factor out the 2. Okay. And I changed it to the purple. All right. So let's do the product rule, right? So now we're going to go find y double prime. So the constant can just go in front. So I'm just going to move it to the front. So we're going to say the first times the derivative of the second plus the second times the derivative of the first. So the first is this guy times the derivative of the second. I think it's just a 1, right? Because the derivative here is 1 plus the derivative of 5. The derivative of a constant is 0. So then 1 plus 0 is just 1. So we kind of got lucky there. So that's the first times the derivative of the second plus the second times the derivative of the first. Okay, so it looks like we got to do the chain rule again. So then the 19 comes down. This x squared plus 10x persists. That's now an 18. And we have to say times the derivative of the inside function, which is this 2x plus 10. I'm going to shrink this down just to get it on one line. And we're going to attempt to simplify this. Now my dog has done all her licking. Now she's back there snoring like a grown man. This is a little chihuahua, mind you, making all these sounds. She's hilarious. My chihuahua teacher. Always teaching me about life. Okay. I mean, she is seriously snoring. Okay. Oh, and we need to close off these parentheses. Kind of like this. All right. Let me see. We got an x squared plus 10x. So we can factor that out. Okay. So it looks like x plus 5. We can factor out a 2 there. Man, this is like, ugh. Okay. So it looks like both terms have this guy right here, right? Let me see. Okay, let me try to account for that. So I'm going to keep my 40. We're going to factor out this x squared plus 10x. Okay. So now, oh, and then they both have 18 of those guys. Okay. So from the first term, it looks like 1 is left over. So we got this x squared plus 10x. Okay. These are gone because we took out 18. Okay. That's gonna, it looks like it's gonna be plus.
I'm in that bitch.
All right, I'm gonna have to. I don't understand why you guys become unmuted. I can make it so you can't unmute yourself. I'll just do that later. Let me see. We could expand that out. That's a x plus 5 squared. That would be what, 38? Let me think. Do I want to do that? Okay. Looks like it's like a 38 times. So it's going to be x squared plus 10x plus 25. I think this is it. Give me just a moment. That looks good. Those are good. That goes with that. Okay. I think this is it. I'm hoping that I haven't made mistakes. Okay, so then if we take it all the way down, we got this 40 x squared plus 10x to the power of 18. If we combine like terms, look, it's going to be 38 plus 1 gives it a 39 x squared. 380 plus 10 is 390. Okay. We got 40 quarters. If we have 4 quarters, it's $1. So what? $10. So that's what, 1,000 minus 50. So 950. Is that right? What do I feel like? We could probably, can we factor out another 39? Hey, Google, what's 95 divided by 39? Sorry.
95 divided by 39 is approximately 2.44.
Okay. All right, so I'm gonna go ahead and look at my prepared notes. Let's see, how do we do? How close did we get? X squared plus 10x to the 18, 39, x squared plus, come on, let's go, 390 plus 950. Come on now, come on. Oh boy, because again, it gets dicey. Like if you're not neat and organized, woo, it's easy to get lost. Easy to get lost in the sauce, right? And you got to celebrate those little ones, man. This world is like real heavy, right? They just take and take and take. You know, I like one of my content creators. I like what he said today. He was like, he's like, get out there. You got to kick this world in the nuts and take what's yours. I was like, that's right. But yeah, so we did it, right? Again, taking your time. And it's a real simple concept, but then it was like, okay, you know, all these pieces, and I am trying to fit it on the screen. This would have been much nicer, like on a dry erase board, something that's big, you know, something that's big and spaced out, and just take your time, and, you know, piece by piece. Anywho, just like for real. I don't know if y'all saw that movie. That movie was decent. It was okay. I like the music, though. The music was fun. It was an interesting story. Okay, this is good. So we got it all the way. But again, it's very easy to make a mistake. This is why I'm like, okay, just do your best. I'm removing a lot of the rigor. My real intent is I just want to expose you to these concepts. I want you to try, and I have to make you accountable on some level, but it's not like we're not in a proctored environment. You're not in an exam room with the proctor with just paper and pencil and a calculator. Like the intent is just to expose you to these concepts and for you to learn as much as you can, but then just make sure to submit what you need, right? So it's the intensity level is drastically reduced, right? Versus if we were in a traditional setting, our exams, you know, proctored exams, only, you know, all that jazz. I'm like, come on, you know. So just, you know, just try to just do the best that you can. Collaborate. Get with the tutor. Make use of my office hours. Text me, email me. Make use of the ask my instructor. You know, just do what you need to do. It's okay. Okay, but yeah, we got it right. So the first derivative wasn't too terribly bad. The second one, you know, is just a matter of being organized and taking your time. Okay. What's the time? Okay, we're looking pretty good. So quick checks I usually leave as an exercise for you. Let's look at this definition. So velocity. The velocity of an object that is s of t units from a starting point at time t is given by this. So the velocity of an object is going to be the derivative of its position function. This is going to be the limit as h tends to 0 of s of t plus h. This basically the limit of the difference quotient definition of derivative, right? But in long story short, when given a function that describes the position of an object, the velocity, which is the rate of change, right, like miles per hour or something like that, is going to be the derivative of your position function, right? So if you're given a position function, you take the derivative that gives you the velocity. I'll just go ahead and say it now. If you take the derivative of the velocity, that's the rate of change of your rate of change. That's going to give you your acceleration. So how fast the speed is changing, right? So the acceleration is the second derivative of your position function. And that's what this is right here, right? So the acceleration is the derivative of your velocity function, which is ultimately going to be the second derivative of your position function, okay? So for this position function, find the velocity and acceleration, where s is the distance from the starting point in miles and t is in hours. Again, miles per hour. So find the distance, velocity, and acceleration when the time is 4 hours. Okay. All right, not too terribly bad. So our position function is given by this. So based on some time in hours, this tells us how far the object is from the starting point. If we want the velocity, that's going to be the derivative of our position function. So that's the 20t. It should be like miles per hour. Okay. And then if we want the acceleration based on time, that's going to be the derivative of our velocity function, which is our position, the second derivative of our position function. In this case, it's going to be 20. That would be miles per hour squared. You can kind of write it like this, miles per hour squared. Those are the units for acceleration. I think this is good. Okay, we got a solid 10 to 15 minutes. We might get out a little bit early, depending on, because it looks like we're almost at the end of this section. And so that's why I keep like coughing a bit, because the sandwich, I think the sauce, it was a delicious sauce, some kind of like garlic something. But I think I'm sure it has some kind of dairy in it. So even though I removed the cheese, I drastically reduced the dairy, but it still it still comes up like this. So yeah. But I've basically been low-key like practicing. It's Dr. Sabi. He was like, if you're trying to heal the body, the illness lives in the mucus. So if you want to heal the body, you got to get rid of the mucus. And he was like, what's the source of the mucus? Essentially animal products. So I mean, I'm not really vegan or vegetarian, but I like to be aware of this kind of stuff. So when I do get sick, I was like, you know what? I did eat that. Let me flush my system. Let me, so at least I can know the cause of it. You know what I mean? And then I just say a prayer when I am like eating animal products, and I just keep it moving, because unless being vegan or vegetarian is going to make me immortal, which is not in this form anyway, not in this body. Maybe it would, I don't know, but I don't know any immortal vegans. So I figured, we're gonna leave these bodies for some reason sooner or later. So just do your best, right? Oh, and then we need to find and then find the distance, velocity, and acceleration after 4 hours. Okay. So the distance after 4 hours, 160 miles. Oh, okay, I get it now. Okay. So keep in mind that this tracks when you guys come and leave. So like if you're just showing up, I'm gonna see it. Like, the best thing is just getting here like 10 minutes early and zen out. Like when I first started teaching remote, I'd be like, okay guys, what do you think? And I'll be trying to like get you guys to talk. But then it was like pulling teeth. It got so frustrating. So I was like, you know what? I'll just, I feel like you guys just at least showing up and just listening on some level is more than enough on my end. And then I just try to keep a rhythm and flow. It was too disruptive for like call and response. I don't mind if you guys like come on the chat and we talk and things like that, but I've gotten used to like, okay, let me just keep the flow. You know what I mean? But yeah. Anywho, 160 miles, right? Velocity. So the velocity after 4 hours. So 80 miles per hour. And the acceleration after 4 hours is 20 miles per hour squared. I'll just put the whole, let's do this. So it was pretty good timing. Let's do something. Oof. Yeah, we're wrapping this up. So I mean, yeah. So right now I'm not going to make too big a deal about it, but the best thing is just if we start at 6, get in the Zoom about 10 till the start of class, and then you can zen out. Like I don't make a big deal about if you're passive, you know. I stop because that was a waste of energy on my end. So I was like, okay, as long as you guys are here, and then keep in mind this is being logged automatically. So, but I know that people pop in and out, and you know it's okay. Like because the technology is kind of dicey like that. So I even have trouble sometimes. I'm teaching and it'll might sometimes either Wi-Fi goes out or this, that, and the other. So I've learned to just like let it go. It's not that serious, and just be available and answer questions and let it go. Okay, I think we're good on everything. This all looks good.
Professor, can you go back one second? I'm writing that last part. My apologies.
You can screenshot it, so like just
Yeah,
screenshot and
I
I'm
got it.
yeah, you good. And I'm gonna make a copy of this available. So
Thank
you
you.
yeah, you good. So when I log out, you know, I'll load a copy of all this stuff. So all the stuff you see me writing, you're gonna get a copy. And again, just you know, don't ever hesitate to just screenshot it if you're trying to get it on the go. Okay. Let me see. That looks good. Quick check I'll leave as an exercise for you, and yeah, that's it. That brings us to the end. Okay, so with the higher order derivatives, all that the main concept, the main takeaway there was that it's the derivative of the derivative. Now we definitely worked a few cases where it got a little dicey. So again, you just gotta be confident, take your time, take it piece by piece, brick by brick, you know, part by part, right? If you try to look at the whole thing, it can be intimidating. But if you say, okay, let me just do this one expression over here by itself. This is the answer that I got. Okay, let me insert this answer that I got. Okay, here's the next part. Let me do this over here to the side by itself. Okay, here's this answer. Let me put it where it belongs. All right, you know, and so that's sometimes why you see me using colors because it helps me to kind of keep track of everything. Because a lot of times when it's monochromatic, then it's like it makes it even easier to lose track of it. Okay, so anywho, are there any burning questions before we go our separate ways? Okay, so we've officially finished chapter 1. All right, that's about the rhythm. We finished chapter 1. Everything is available in Pearson. So with Pearson, I want to say that all assignments for the entire semester are available right now, with the exception of exams. So what that means is that you don't have to wait for me. You don't have to wait for us to meet, because again, anything that I intend to save live is already available in my recording. So there's nothing stopping you from using my recordings, getting ahead. And honestly, you can go ahead and finish all of your assignments for the semester, and then you're just waiting on your exams. Just show up, get your attendance. You know, you can zen out. I don't make a big deal about that. So as long as you're getting your attendance credit and you're submitting your assignments promptly with satisfactory scores, that's all I'm really looking for on my end. And then, you know, hopefully on your end, you're learning as much as you can. Okay.
Professor, did you already take attendance?
Yeah, so that's taken automatically, right? So as you pop in and out, it shows me when you guys come and go. So
Okay, I'm just now Morehouse just unlocked my account, so this is the first session I was able to actually attend. So I was just
yeah, it's okay. So yeah, you good. So like,
thank you.
yeah, you good. So that was part of the disclaimer I made because I was like, sometimes this technology can be unreliable, so it's okay. Don't worry about it. And again, it's still kind of early in the semester, so you know I understand that we're still like getting the rhythm, getting everything down. So, are there any other burning questions before we go our separate ways? Going once, going twice. Forever hold your peas and rice. All right, gentlemen. So what that means is, you know, over the weekend, you know, do your best to try to keep up. Try to finish out chapter 1. Next week, you can expect us to get through 2-1, 2-3, 2-1, 2-2, 2-3, and 2-4. So if you feel up to it, go ahead, watch the recordings for up to 2-4, and go ahead and do those corresponding homework so you can get ahead, right? That way, when we meet next week, it can be a review. Idealistically, if not, I totally get it. Just do your best. All right, gentlemen, if there are any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, have a great weekend, and we're going to meet back on Monday, same time, same place to begin chapter 2 for the next installment. All right, guys, take care and peace. Yep.
Thank you.
Yep, my pleasure. All right. So I got my homework. I need to update my attendance and what else? Make these notes available. Okay, guys. I actually got energy today. Oh, I ate. That's why. All right, guys. Let me check the chat. No, it's okay. It's okay. I had to remind myself that too, because again, I am monitoring when people come and go, but then I forgot. I had to remember, like, sometimes this technology it can be unreliable, so you gotta kind of be general. So anyway, all right, guys, have a great weekend.